All right, so we have Gauss's law, but have no sense yet of how we use Gauss's law. So we have the flux equation, E dot A over some surface is equal to the charge enclosed over epsilon naught. And our goal is to use this to find this E, which is a weird kind of goal. Because when you solve an integral, when you set up an integral, you're not generally using it to find whatever's inside the integral, the integrand. In fact, you could argue that you often can't do that. There are integrals where the answer is 0, but you don't know what's inside here. It doesn't have to be 0. That's inside there. So this is not an obvious program. So what we're going to do is do this with an example. So here, the idea is I have a very long, infinitely long, but really, really long charged insulator, like a long pole, a PVC stick or something like that, that's charged uniformly, the same charge all the way down. And so we're going to say, because it's so long, we're going to talk about its charge density. So that would be lambda, so that would be how much charge per length it has. Okay, and so maybe this is some number, 4,000, 15 micro coulombs per meter, whatever it is. And the question we're going to ask is, what is the electric field outside of this line of charge? Now, we know that we can actually do this if we take this and break it into little bits. We set up, we say, what is our electric field? Suppose we want to find our electric field right at X marks the spot. That's what we often do. And so we start to say, well, let's draw, let's say what direction this points. So if we say this little bit of charge here, that's going to give me an electric field that points this way, right? This little bit, dE, due to this little bit. And if I have another little bit of charge, say right here, then that's going to give me an electric field that points in this direction. It's a little closer, so this gets bigger, right? And so forth. And we add all these vectors up, and we do some kind of integral, and everything is fine, except the integral isn't easy to do. And I promised in the last video we were going to avoid doing the integral. In fact, we're going to avoid doing this integral or the one that we might need to do using that. So in order to do that, we first need to figure out what direction the electric field is likely to be. So this gives us an idea. So I've got these 2 points here. If I want to find the electric field here, let's at least establish what direction it's going to be. And one thing we can realize is, this is sort of the halfway point, that if I've got a charge down here, then an equidistance from this point, sort of from the middle up to here, is another charge that's the same distance away. That's maybe a little more. And gives us a dE in that direction, so that these 2 arrows cancel out, and I just am left with an arrow to the right for that one. Similarly, for this charge, that's pretty close to my midpoint right there. That's my midpoint. Then I have another bit of charge there that gives me an electric field that just barely points down like this. dE, oh, it's a little longer. And these 2 green ones cancel out to give me sort of a bigger field, but still towards the right in that case. In fact, if you think about this being a nice column, you can imagine, in fact, from wherever you stand from this column, the electric field points away from it, sort of directly away, not up or down. So if I'm standing here, the electric field must point in that direction. If I'm up here, the electric field points in that direction. If I'm standing where I am right now, then the electric field is going to point sort of in that direction, okay? Or in this direction as I move around. It's kind of hard to do on the video, but where my hand is, notice this is then the direction that the electric field points. Okay, so we're going to get back to finding the electric field at X marks the spot. We know the direction is like this. Okay, so we know the direction. Now what we want to do is set up an arbitrary surface, and we can do any kind of surface. And the rules for building this surface, so we're going to draw a surface. It's called a Gaussian surface, where we can find the flux, but we want to draw a special kind of surface. We want to draw a surface that matches the symmetry. That's a fancy way of saying the same shape. And is such that the electric field is constant on this surface as much as possible. In other words, we could draw, for example, so this is a cylinder, so I could draw a cylinder. So I could draw a cylinder like this, right? Now, this has a couple of problems. This matches the symmetry, so that checks off. But we also need it to hit the point where we want to find where we're looking for E, or where X marks the spot. So I need to make this a bigger cylinder, but I also want to keep it centered on this. So instead of this little cylinder, I want to have a cylinder that goes out to here, but I still want this to be centered. So this is a very big cylinder all of a sudden. So I'm going to draw like this. Okay, and we still have our lambda, which is our charge per length. Okay. So here's our mythical surface. And I've gotten rid of our smaller surface. And I want it centered on this because I want the electric field everywhere along this outside ring of the cylinder. I want to be the same distance away from the ring. So every point on this outside ring, if I'm like this, anywhere along it, if I'm over here, this is the same distance away. If I'm somewhere else on the side, I want it to be the same distance away, because then I have some hope of saying this is a constant. And constants I can pull out of the integral. So that's the heads up of where we're going. All right. That's the hard part of Gauss's law, is drawing this magical surface, because it's like, what am I doing and why? And I really want to hit the points where I'm interested in the electric field. So if I'm trying to find the electric field here, that's got to be on the surface. And the surface needs to be centered and matching, be basically the same shape as whatever I'm wanting to draw. And I'll just say it only works for a couple of instances. Okay. Then what we're going to do is we're going to focus on this side of the equation first, the blue side, and then we'll look at the orange side. So the blue side of the equation says that I've got to find this E dot dA. So that means I need to know something about my A. Right? Now this is a curved surface, a cylinder. So right here on the edge, that's the direction of A. Right? Down here, this is the direction of A. If I'm going around this cylinder, then this is sort of a curved surface, right? A sort of points out this direction, right? But E also points out. If I'm on the back side, I can go this way and do the same thing, okay? So all the way on this curved surface, I'm going to argue that these are in the same direction, which is nice because on the side, we say E dot dA, and so I should really make these little tiny areas, dA, 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 because it's really this curved surface on the curved little tiny square on the surface, that this is just equal to, the angle between these is 0, so this is E times dA times the cosine of 0 degrees. Cosine of 0 is 1. So on the side, we just have E times dA is what's inside this integral, okay? That's not the flux yet, but that's what's inside. I'm going to look at the top now. So the top, notice the area goes like this. This is my little dA on the top. And my electric field at this point still points out this direction. I'm closer in, so it's a bigger electric field than it was out here. So E dot dA on the top, notice the angle between them, 90 degrees. So E dot dA, my little bit of area on the surface, that little square patch on the surface, is going to be E times dA times the cosine of 90 degrees, and that's equal to 0. So my integral that I'm going to do, and we write it actually with a closed loop to say we have to do the entire surface, this integral E dot dA is equal to integral of the top, E dot dA, which is 0. We don't even have to do the integral because this dot product, this inside thing, is 0, plus integral E dot dA for the side, which we know is E times dA times cosine of 0 degrees on the side, plus integral on the bottom. And on the bottom, we get 0 as well because our dA points down, our area points down on the bottom, and E still points along the surface. So there's no flux. The other way to think about this, there's no flux through the top and bottom surfaces because the electric field points out in all cases. So all we have to do is this piece. So this becomes this integral. Now my claim is, and this is why we needed the nice symmetry, is that the electric field, the magnitude, the direction changes as we go around, right? This is the direction that it points. Here's my, sorry you can't see it, it's black, but here's my direction, okay, of the electric field. That the value, because everything on this surface is the same distance away from that. If you're the same distance away from the same charge, you're going to have the same electric field, right? If you're closer in, it's stronger, but if you're the same distance, if this point is 1 meter away, it doesn't matter if you're 1 meter away on this side or 1 meter away on this side or 1 meter away here or 1 meter away on that side, you still experience the same field. And so this becomes now the side E, because it's a constant, E, the magnitude of the electric field, times dA, the magnitude of this becomes E side dA. So this is a constant, has a constant value. Okay, now we have an integral to do. And you're like, I've never taken an integral of an area. Well, actually, that may not be the case. If you've had a little more than Calc 2, you may have done this. And even maybe sometimes in Calc 2, depending on how it gets set up. But the integral, if we just have something that looks like integral dy, just call it a variable, that is just the value itself, right? Integral dx is equal to x. Integral dy is equal to y. It doesn't matter. So in this case, this just becomes area, or the area of the side. So the flux through this surface, in this case, is just equal to, the total flux is equal to the electric field times the area of a side. Okay, so this is a cylinder. This is a, if you like, this is a piece of paper that's rolled up in a cylinder. It's just the side. So to find the area, it would be the height times the circumference. Okay, so that area would be the height, h, times the circumference. The circumference is 2 pi r. The h must be this height right here. Okay, that's the flux. So that was a lot of work to find this left hand, the blue side. The next step is to find this, and it doesn't have to take this long and normally when you're doing these kinds of setups, but I just want to make sure everything's fairly clear as we go along. Okay, so we've done the hard part of Gauss's law. We found out what this integral is. We really only had to find the integral of dA, which was A, and that was our area of just this side part. We didn't have to do the top and bottom because E dot dA was 0. Now we just need to find out how much charge is enclosed. And so this lambda, so I'm doing the orange part now, so lambda is charge per length. So if I want to find out how much charge, like if I have 4 coulombs per meter and I say I've got 2 meters of length, then that's going to be 4 times 2, which would be 8 coulombs, right? So that's not very hard. In this case, the length that we have enclosed, so the amount of charge inside this surface is going to be lambda times this h, because that would be charge per this length or height. So that would be the charge that's inside the cylinder that I drew. How big is this cylinder? I don't know, it's a size H. Give it a number if you want, 25 centimeters. I don't care. And so I'm going to put that in, so that's going to be lambda times H. Now I can solve for the electric field. I've got electric field is equal to lambda H divided by 2 pi RH. The H's cancel. This is the value of the electric field. The electric field is the charge per unit length, 4 coulombs per meter if you like, over 2 pi r. That's the magnitude. The direction is out, right? Radially out from the direction is out. Points away or away from this post or this rod or this wire. So this could be, for example, the electric field of a wire type situation where it's really, really long. Now, why did I need for it to be really, really long? That had to do with what we did at the beginning to say that my electric field points in this direction because any charge up here was balanced by another charge down here so that the electric fields would both cancel out and go that way. So that's sort of the symmetry picture. What that lets you know is that this is only useful for a couple of situations. One is when we can set up a cylinder, another is where we can set up a sphere, and another is when we can set up a really big plate. So we'll look at some of those examples, but this gives you a way to do an electric field that almost completely avoids doing an integral. The integral that we have to do is an integral of dx equaling x type